You see? So of course, to do this job, these people did not use a single computer, but they used a graph of many computers. But still, it took, I think, like 2 years for them or so. The largest RSA number which has been cracked is the RSA 768, which has more than 200 digits in decimal. This is the number. The same rule starting from here up to here. And for this one, which is larger than the other one, the same estimation of CPU time gives 2,000 years on a single computer. So impossible to do that. Okay, so to see how hard it is. So not speaking about this one. It requires the same estimations will give like the age of universe also. Billions of years on a single computer to do the task. So that's why it's very secure. Even if you use a lot of computers, I mean, some group or a state or a company or even, I don't know, hackers, a group of hackers want to do that. And even if they use dozens of computers, they will not be able to find the P and Q and then to crack the code. So this is the difficulty in cryptography. Okay. Okay, I'm ready to start the third lecture. I don't know if Malik is coming. If not, we will start, and he can join later. Sorry? I didn't. I saw him like 15 minutes ago. Maybe he's around. What did you do your hair? So Malik is coming, so we can wait for a couple of minutes. So in the meantime, if you have any question, please go ahead.
Yeah, I want like, are we gonna show us the relationship between conducting materials and quantum computing?
Yes, this is a very good question. It's about the hardware. So how to build up a qubit. not just the concept or the scheme or how it works in theory, how does it work in real life. And one of the best working qubits are based on superconductors. So it's what is called the transmons. It's a superconducting circuit. Basically, it Josephson junction, so that the pair of the Cooper pair of electrons can be on one side or on another side, and this represents the two states, 0 and 1. Okay, so you can build up circuits like that. It is not very easy because it requires, in addition to the technology of superconductors, cryogenics, because you have to have a very low temperature, like helium liquid cooling, and so on. So this is the most obvious the hardware part. The implementation, and I will show you an example of, photos of real processors, quantum processors, those of IBM. And they are based on superconducting. This is this.
Can I ask a question?
Yeah, sure.
Example.
Yes.
What's the difference between normalized function and exponential?
Well, in quantum mechanics, basically what you do is to describe the behavior, the dynamics of the particle, even free or under some interaction. So for that, quantum mechanics, you describe it with the wave function, which is a function depending on the space coordinates and time, and this function is a solution of the Schrödinger equation. And this is point 1. Point 2, what is the meaning of this wave function? Is related to the physical properties of the particle. Following the Max Born interpretation, the square, the norm of the wave function, represents the probability density to find the particle in some point in the space. Okay. So this is a probabilistic description of the behavior of the particle. As it is probabilistic, if you sum all the probabilities over all the possible events, you should find 1, because all the probabilities are between 0 and 1, and the sum of them should be 1. That's why when you sum the square of the wave function all over the space, you have to find 1. And this is what we call normalization. That's why the wave function should be normalized. This is the first point, the first question. The second one, the orthogonal states. Here we are dealing with a particle or some property. It has several quantized possible values. So the simplest example is a particle in a box and several quantized energies. To each energy, there is a wave function associated to that. Okay? Psi 1, psi 2, psi 3, etc. Okay? And mathematically, you are working on what is called the Hilbert space. Hilbert space, it's a vector space, space of vectors. And one of the properties of the algebra of this kind of spaces is that these eigenstates, these eigenvectors or wave functions, as they are associated to different eigenvalues, should be orthogonal. So orthogonal can be understood as belonging to different states. So all the wave functions associated with different levels are orthogonal. And this is very good property to make the algebra very easy. Is that okay? And yeah, please.
Yesterday you said that position matter. So in the final equation of the trigonal system, the system is the trigonal system, right? If we put the PV will be in the class of the PV in the class of the HS. Are the system can be or not?
Okay, I see. You speak about the superposition of
Yes.
states. Actually, the algebra I'm talking about is linear. So a cat written like HH plus VB is exactly the same as VB plus HH. It doesn't change anything. Okay? Hi, Mary. Should we start now?
Yes, please. Yes.
And if you have questions in the meantime, please do not hesitate. It's also an opportunity to discuss and we will go in depth with these concepts. So after the lectures of yesterday and having enhanced the tools, I hope, of quantum mechanics to understand how the quantum circuits will work, let's go now into some details. Yes, so I started yesterday a little bit speaking about the quantum supremacy. By the way, there was a like kind of controversy, Malik, kind of political controversy about this word of supremacy. Maybe here it's a good context and to speak about. So now people are speaking about more about advantage, which means once again in some specific task. The best classical computer in the world cannot handle the problem, while a quantum computer can solve it in a reasonable amount of time. This is the definition. And this was proven by the people from Google. So here, a snap of their paper published in 2019. And here I'm just I'm quoting some key sentences from their abstract. So here the authors of the paper are speaking. So the promise of quantum computers is that certain computational tasks might be executed exponentially faster on a quantum processor than on classical processor. What means here exponentially? The numbers I told you yesterday and I have shown this morning. So instead of thousands of years, or millions of years, you reduce the problem to seconds or minutes, or even hours is okay, hours. So this means exponential and how it grows with the size of the problem. So a fundamental challenge is to build a high fidelity processor capable of running quantum algorithms in an exponentially large computational space, increasing the number of qubits. So here the authors are speaking about their achievement with which they were able to show for the first time the advantage, the quantum advantage. So they say here we report the use of a processor with a programmable superconducting. Who asked about superconductors? The left. Okay. So with programmable superconducting qubits to create quantum states on 53 qubits corresponding to a computational state space of dimension 253. Okay, so in blue, I think the main point here. So the Sycamore, the processor, the quantum processor called Sycamore, this is the commercial name of it, takes about 200 seconds to sample one instance. So this is it's a sampling problem on a quantum circuit 1,000,000 times, while our benchmarks currently indicate that the equivalent task for the state-of-the-art classical supercomputer, not a simple laptop, would take approximately 10,000 years. So this is what we are speaking about. The power of quantum circuits. Here you have a picture, a real picture with the size. 1 centimeter, so it's almost 2 by 2 centimeter, 1 inch, more or less. And this is the scheme. What is behind that? These are superconductors. Inside very small, of course, miniaturized superconducting circuits, symbolized here with these crosses. And why it is 53? Actually, it should be 54, 9 by 6, but one was not working, so it's 53. Okay? And with this circuit, quantum circuit, Sycamore, the group, sorry, it's not IBM, this one is Google. We show IBM next. Google were able to show the quantum advantage. So in the meantime, other companies are running also the same race. And if you remember, probably you remember in the first lecture, I talked about this IBM 400 plus quantum bits, qubits, Osprey processor. They just announced it a couple of months ago. So you see that people are making huge steps toward the universal, maybe thousands, maybe more. This morning I was reading a new breakthrough in the news announcing the possibility to have in a reasonable time like 1 billion qubits on a chip. And it's really exciting. So there's some details of the hardware. And basically they are using superconductors. So now, just to make here your superconductors, they are here. You missed the point here. This is the Google Sycamore quantum circuit with 53 qubits based on superconductors. This is the real photo, it's the real picture. And this one is of the most recent released quantum circuit by IBM with 433 qubits. Sure.
Just to add on what you mentioned, this is a really, 200 seconds instead of 10,000 years. This is awesome.
I thank you very well. I'm in general a skeptic of a scientist.
This is outstanding, and material science is the cornerstone of this. I think just to add on what you have mentioned, is that first of all, who is working on superconductivity? Who has some background in superconductivity? And also IBM in relation to this type of new microprocessors have demonstrated and built a new generation of memory stocks, which are vanadium dioxide based. Who is working on vanadium dioxide? In addition to that, these microprocessors are, as you mentioned, superconductors. And therefore, the heat has to be removed at maximum from this. And who is working on nanofluids, please? So you would see that in fact that this should appeal to all of us.
Sure.
Thank you for telling me, please.
Thank you.
Now I believe that as Nelson Mandela, when he stays in peace, said, all seems impossible until it's done.
Yeah.
And it will be done soon.
Yeah.
Thank you.
Thank you. Thanks a lot.
This is impressive.
Okay, so let's move now to the gates. Just one slide to remind you, maybe most of you already know what are these logic gates, the OR, the NOR, the AND, etc., which are the basic tools to build up circuits in electronics, microelectronics mainly. Okay, you have more details in the appendix. And let me take again the half adder circuit we talked about yesterday. say the same points. And this is the quantum circuit, which is intended to do the same task to make the half addition. So the question I will start with today is how to build up this quantum circuit first, and then second part, how does it work? So what is the input and what is the output and what is the role of each part of it? Okay. So first of all, what are the quantum gates? Let's start with the simplest ones, which are the 1-qubit quantum gates. So a quantum gate actually is a unit transformation that transforms the quantum states of input qubit to another quantum states or an output qubit. So what you can imagine, you have a qubit, let's say a superconductor, or two-level system, whatever it is, with two states, 0 and 1. This qubit is in one state, it may be 0, 1, or any combination of both. You operate a unitary transformation on it, like it can be a microwave pulse or something like that, which physically changes the state of the qubit. So this is called unitary. This is described mathematically by a unitary transformation, and this is what is called a quantum gate. Okay. So a very simple example in usual electronics, everyone knows the NOT gate. So the NOT gate, if the input is 0, the output is 1, and if the input is 1, the output is 0. It's just a reverting operation. So the equivalent in the quantum circuit is the Pauli X gate, which has exactly the same table of truth. Okay, and you will see later what is the matrix describing it. So this example and many others are actually, all the 1-qubit quantum gates are represented by unitary matrices, 2x2 matrices. So let's review them. These are the most important ones. X, Y, and Z Pauli gates. Maybe you remember yesterday I talked about the sigma X, sigma Y, and sigma Z Pauli matrices. These are exactly the same, just the name is changing here in the context of quantum computing. The Pauli matrices are called X, Y, and Z instead of sigma X, sigma Y, and sigma Z. Another very important gate, H or gate or Adamar gate, rotation with angle phi gate, and other gates, IST, and the general gate U3. Well, each of these gates is described by a very simple matrix. I will show the ones in blue, which are the most important, and you have an appendix for the others. And for all of them, I'm using this kind of graphics, and I already told you that I am taking them from the IBM Qiskit platform. I hope I will have time to show you. We have, obviously, we are connected here, so I can go to this site later on and show you. So this is the way we represent the gates. At the left, you have the input qubit, Q, if it is only one or several ones, Q0, Q1, etc. This horizontal line and a symbol for the gate. So you will see this kind of things many, many times today. For the X, Y, and Z gates, the matrices are here. You have already seen them. Okay, this is the NOT gate. This is the sigma Y Pauli matrix, and this is the Z matrix. So what does it mean? I mean, let's try to apply one of these gates to a qubit in a state. So by default, in general, if not specified, all the qubits in the quantum circuit at the initial stage are supposed to be in the ground state. All of them are initialized to value 0. So if I take a qubit in ground state, in 0, and I apply an X gate, what would be the result? So as you can see here, 0, the result will be the state 1. So the action of X gate is simply the transition from the ground state to the excited state. Very simple. And what would be the action of X on the excited state? The state decays to the ground state. Very simple. It's an inversion. Ground becomes excited, and excited becomes ground. So 0 becomes 1, and 1 becomes 0. And the same thing for the others, except the Z matrix, which is the default choice and convention in quantum mechanics. The Z is the quantization axis, so that's why the Z matrix is diagonal here. So 0 and 1, the states 0 and 1 are the eigenvectors associated with the eigenvalues +1 and -1. Please note here that you will find in the textbooks always the matrices in quantum computing uses a specific notation for the parentheses rather than the traditional ones. This is just a detail which is good to know. Okay, so now the Hadamard gate. Hadamard gate is described by the following unitary matrix. It is easy to check with some algebra that it is unitary. You take the H dagger and you multiply them and you will find a unity matrix. So the same question, what would be the result of applying Hadamard gate to a qubit which is initially in state 0? Okay. So all you need to do is just to multiply this matrix by a vector 1, 0. Very simple vector. So any student, graduate student can do the calculation. And the result is in the first column, of course. So the result will be 1 over square root of 2, 0 plus 1, as you can see here. So the Hadamard gate applied to the ground state will give you what? Will give you a superposition. So this is the key word. It's not like X gate, just an inversion. 0 becomes 1 and 1 becomes 0. No. Here, Hadamard gate plays a very specific role, which is the creation of a superposition state. This is how superposition state is created in a qubit and how it is implemented. So H applied to 0 gives this linear combination, 0 plus 1, normalize it, call it state plus because of the sign here, and H applied to 1 gives the other combination sign minus, which is the minus state. So that's why Hadamard gate, you will find Hadamard gates in almost all the quantum circuits, because it is the gate that creates superposition. And yesterday I told you that 2 main points in quantum computing are let's check, superposition and the other mysterious property of couple of particles, entanglement. Yes, good. So superposition and entanglement. So we have to know how we are able to make superposition and entanglement in quantum circuits. So are you following me right now? Okay, good. So some exercise, some practicals for the students. You can show this is just some algebra that the X gate can be simply the product of H by Z by H. This is simple algebra and multiplying 2 by 2 matrices. Okay. Well, so this is the way to manipulate one single qubit. But this is not enough. For instance, to create entanglement, I think everyone understood that we need at least 2 particles, 2 qubits. Okay? So we need a kind of quantum gates that acts on more than 1 qubit. So we are speaking here about n qubits quantum gates. And let's start with n equals 2 and 3. And actually it will be enough. So the most important are 1, 2, and there is one single 3 qubit gate called the Toffoli gate. And with this you can build the main quantum circuits you need or which are used today. Okay. So let's start with 2 qubits, which we will note here. So we do not have any more only 1 qubit, we have 2. So the rule is to start with the 0, so Q0 and the Q1. If we have more, it will be Q0, Q1, Q2 up to Q1. Okay. So if you remember yesterday, I already introduced the kind of tensor product, which means that the state of the system is simply the product of the state of qubit Q0 by qubit Q1. Okay, so we have 2 qubits now. And to make the notation more light, I remove all these symbols. I just keep Q1 and Q0 with this convention for the order. So now I have 2 qubits. The easiest thing to do is to see how to construct operations which act on one of the qubits and not on the other one, before introducing an operation on both of them. And let's take this example. For instance here, so I think everyone now understands well, I have 2 qubits, Q0 and Q1, in state 0 by default. If there is another state, it can be specified. To Q0, I apply Hadamard gate, and for Q1, I apply X gate. So what would be the results? So we have already seen in the previous slide that how Hadamard acts on the states of Q0. So if it is 0, I will have the state plus, 0 plus 1 normalized, and if it is in state 1, I will have 0 minus 1 normalized, while for the X gate will just revert the state. If it is 0, it will be 1, and if it is 1, it will be 0. So to be able to describe this with the algebra, we use the tensor product of operators, which means, for instance, here, this circuit is described like this. So X tensor H apply to Q1, Q0, which means X acts on Q1 and H acts on Q0. And it is independent, so that the result is that X acts on Q1 independently of H, which acts on Q0. So what I may ask you to do now is to try to guess the state here. If Q0 is in state 0 and the Q1 is in state 0, what would be the state of both qubits after applying the gates? Can you try just to write it down so that you can check on the next slide if you are right or not? So Q0 is in state 0 and Q1 as well is in state 0. I may help you by reminding you what was in there. So this is the result of applying H to state 0. So this is the answer in our case. Okay. Did you find it? Yes, good. Okay, thank you. So for x applied to state 0 will give you state 1. Okay? So what we should expect here is that we will have state plus linear combination for qubit Q0, tensor product with state 1 for qubit Q1. It's as simple as that. So another way to write the same thing is to calculate the tensor product of X and H following the tensor products of matrices, which is a little bit more complicated. I will skip it. I do not really absolutely need it now. We can skip it. Yes. Okay. So now let's move to another gate, very important gate. You have already seen it on some examples I have shown yesterday. What is called the C0 gate. C0 gate or CX gate or controlled NOT gate. It is a kind of gate acting simultaneously on the two qubits, okay, Q0 and Q1. One of the qubits is playing the role of a control qubit, and the second one is the target qubit. We have a control and a target, which means that depending on the state of the control qubit, something will happen or not to the target qubit. This is what it means. To be more clear about that, so this is the matrix representation of the C0 gate. Obviously, as we are dealing with two qubits, the matrices are not anymore 2 by 2, but be 4 by 4. This is clear. And what is precisely the action of the C0 gate? It's a conditional gate which causes a state X to act on the second qubit target if the first qubit Q0 is in state 1. What does it mean? Here for a qubit Q0, you have two possibilities. Q0 can be either in state 0 or in state 1, okay? Or in any combination. But let's take this basis representation. If Q0 is in state 0, this means that this qubit is not activated. In this case, nothing happens to state Q1. So to qubit Q1, sorry. So the qubit Q1 will stay in the same state as it is. If it is in 0, it stays in 0, and if it is in 1, it stays in 1. The second case is if Q0 is in state 1. In this case, we say that Q0 is activated. If the control is activated, the state of qubit Q1 will change, following which rule? Following the X gate rule. So its state will be reverted. If it is in 0, it will be in 1, and if it is in 1, it will be in 0. And the matrix here is very clear about that. This is the identity for the qubit Q0 and the X gate for the qubit Q1. Okay, this is the controlled NOT gate. With this, we can already start constructing our first quantum circuit. Very simple one, but an important one. With a focus on entanglement, of course. So let's do the following. I consider, you will do the exercise with me. We consider two qubits, Q0 and Q1. And the rule, as I said at the beginning, by default, the states of Q0 and Q1 are 0. So Q0 is in state 0 and Q1 is in state 0. So the state of the system before applying any gate is 0 tensor 0 or 0, 0 in simplified notation. Okay? You can just note that. And so this is the initial state. I do not have a blackboard, but the initial state will be 0, 0. Okay? You can understand it even with without a blackboard. I mean. Okay. And let's apply an Adamar gate on qubit Q0. Okay. What would be the result? It's even simpler than the last exercise. Since we know now that Q0 will be transformed, 0 will be transformed in plus state, while Q1, there is nothing here. So if it is in 0, it will stay in 0. So the result would be plus state for Q0 multiplied by 0 state for Q. Then we apply a C0 gate. C0 gate. Okay? And remember how the C0 gate works. Depending on the state of the control qubit Q0, if qubit Q0 is in 0 state, nothing happens, the gate is not activated. But if Q0 is in 1 state, you apply an X gate to the second qubit. And the question now, what is the state here after applying the first Adamar gate followed by the C0 gate? Once again, try to make the exercise of this, if you like, of course. But this is generally what I'm asking to my students in the classroom. You can just try. I can help you if you like. So in the first step, we applied H to Q0 and identity to Q1. Then we applied C0 gate to both of them. So the first part, before applying the C0 gate, the result, as you already found, is 0 for qubit Q1 and the plus for qubit Q0. Here, just I have to mention that in IBM Qiskit, the order of qubits is reverted when writing it. So that's why 0 here appears before plus, but this is only a detail. More important is when you apply C0 to this state. Because if you develop a plus as 0 plus 1, what will you find? 0, 0 plus 0, 1. Okay? It would be much easier with the board. I'm sorry for that. 0, 0 plus 0, 1. And the C0 gate for each part will see what is the state of the control qubit. So 0, 0 plus 0, 1. In the first case, the control qubit is a state 0, so it will not change. It stays 0, 0. For the second one, it is 1, so it changes the state of the second qubit from 0 to 1, so we obtain 1, 1. And the final result here at this level is 0, 0 plus 1, 1 normalized. This is the final result you should get. And what is the importance of this state? Have we already seen this thing yesterday? With VVHH, or we were talking about. This is exactly what we were dealing with yesterday. This is an untangled state. So this is how, in quantum computing, we create an untangled state between two qubits by combining a Hadamard gate, single qubit Hadamard gate, with a controlled NOT qubit, 2-qubit gate on the system afterwards. Okay, is that clear for you?
Yes.
So of course, if this was your first quantum circuit, okay? But then, as you understood the rule, you can play with this, and instead of applying only one Hadamard, you can add another Hadamard gate here, or X, or Y, or Z, and see what happens. So, for instance, if you add before applying, this was the previous circuit, okay? We just did. Now you may add a Hadamard here, make the calculation, see what happens. So you can obtain another entangled state, more complicated, with a combination of 0, 0, 0, 1, 1, 0, and 1, 1. This is one of the so-called Bell states. Next, what you can do is just to add other gates and so on and so forth. This is amazing if you take a C0 gate and put it like a sandwich between two pairs of Hadamard gates. You can check this easily. You obtain a C0 gate inverted, which means that the control qubit is no more Q0 but becomes Q1, and this may be useful for practical sub-practical tasks. This is called the phase reversal. So finally, for the gates, the other important quantum gate in quantum circuits is the so-called the Toffoli gate, after the name of the guy who invented it quite recently. It is like the C0 gate, the controlled NOT gate for 2 qubits, but this one has 2 control qubits instead of 1, and a single target qubit. So how does it work? The same principle. The state of the target qubit will change if and only if the 2 control qubits are activated. Okay. If both are not activated or one of them is not activated, nothing will happen to qubit Q2. You need both to be activated. That's why it is called the CC0 gate, or more commonly, the Toffoli gate. Okay. So what these kind of gates are useful for? Actually, these gates will replace the AND and NAND gates, very well known in computer science and electronics to implement the basic operations of addition and so on. So some exercises. Okay, so now we have the gates. We can move to the circuits. And before showing one example of them or two, let's see some general considerations, some definitions. So a quantum circuit obviously is a quantum device which consists of a succession of coherent operations on qubits of a concomitant classical calculation in real time. So I will comment on this last part of the sentence later on, but the main idea is that you construct, you build up your quantum circuit with a certain number of qubits and gates, succession of gates. Okay, very basic. But this is not enough to have a full quantum circuit, because you make, okay, you have a certain number of qubits, 1, 2, 3, 4, whatever, much more like we have seen on the circuits I have shown in the beginning. So you have an initial state, then you apply the quantum gates, but at some moment you need to get the results. So how does it work? We are speaking about quantum mechanics, and we are following the evolution of state. All what you can do at some point in quantum mechanics is to make a measurement. So you measure the state of one or more qubits. And when you make a measurement for the state of one qubit, what can you find? What are the possibilities? So here, once again, we need the postulates of quantum mechanics I told you about yesterday, which says in a specific case that when you measure the state of qubit, whatever the state is of the qubit, you cannot find anything but 0 or 1. So at the end of the day, the result you get is 0 or 1. So what is the importance of the quantum state? The quantum state monitors the probability that you find 0 or 1. So if the qubit is in state 0, you will find the value 0 with 100% probability. If the qubit is in state 1, you will find the value 1 with 100% probability. If, and this is the more general case, the qubit is in a superposition of both, with alpha for 0 and beta for 1, you will have alpha squared probability to find 0 and beta squared probability to find 1. And alpha squared plus beta squared, of course, equals 1. This is why we need absolute normalization. Okay? So in the simplest example, in the plus state, for instance, where the components of both vectors are exactly the same, 1 over square root of 2, the probability in this case to find 0 or 1 is 50% for 1 and 50% for the second. And this may be quite confusing. Why? When you want to make a very simple mathematical operation with your smartphone or with the calculator, you just want to calculate 3 plus 4. What would be the result? I mean, 3 plus 4. It's 7. If you do it again, second time, what would be the result? Can it change if you do it twice? It will be 7. And if you do it 1,000 times, it will be always 7. In the quantum world, things are different. So if the qubit is in a kind of combination of the two states, and you make the measurement, you may find 0 the first time, the second time you may find 1. The third time you may find 1 again, and 0 and 1. But when you make a large number of measurements, you will, at the end of the day, find 50% of the measurements giving 0 and 50% giving 1. So imagine that you have a kind of quantum calculator, 3 by 4, okay? Not by 4, plus 4. First time you may find 7, second time you may find 6, then you may find 8, or 9, and this is confusing. So how does it work finally? Actually, the key point is that you need to repeat the process a large number of times, and if you do that and you draw the histograms, you will see in this, of course, imaginary case, you will find a peak, very high peak of the value 7, the most probable one, and small peaks for 6 and 8, etc. And you say with large complements, the result would be 7. This is one of the main differences between the way a classical computer or processor and the quantum computer works. So what you need actually is to make the calculations a large number of times. Okay? That's why in the circuit you have the quantum gates. You need to make the measurements at some point, and you have to do the job again. So you need some resets to redo the calculations a large number of times.
Is it possible?
Sorry?
Is it possible?
It is, indeed.
So it's probability. What if in the reality it becomes the small ratio, the small probability?
Yes, you can trust because you know that if the number of measurements goes to infinity, the probability of the most of the actual result will be very, very high. Okay?
Is there any limit to accept the answers?
Yes, of course. If you can run some examples on the Qiskit platform. By the way, the minimum number in this platform is 1,000 times. But if you do the calculation, let's say 10 times, you will see that almost all the values have the same probability. So you cannot decide. It's not reliable in this case. So one of the conditions to make it reliable is to make the calculation a large number of times. Of course, you can see we are losing our time because with a classical computer, I do the job only once. While for a quantum computer, I have to run the algorithm thousands of times. That's true, but this is a very fast operation actually. It takes, I don't know, a microsecond for one operation. 1,000 times, it's no more than a millisecond, and at our scale, it is still very small. But this is not the main point. The main point that the quantum computers can solve problems that classical computers cannot. This is the main point. Okay? So the cycle is as the following for any quantum circuit, like the ones we will see in the second part. First, initialize the qubits. So by default, they are in 0 state. Reinitialize in the second and the other iterations. Apply a succession of unitary transformations using the quantum gates, making the measurements. So the measurements at the end of the process of one cycle are no more quantum. Okay? The state is quantum, but when you make the measurement, once again, what is the output of the measurement? What you find? Is 0 or 1. These are, numbers we are used to. These are classical numbers, classical information. It is no more quantum. Because when you make the measurement, you destroy the quantum state. So then you can write it just or store it in a classical register. So either it is your final result for some algorithms, or you have to manipulate it at some time and, for instance, for a variational calculation, change a little bit the conditions and do the job again. So examples of quantum circuits, the half adder. So now you understand better, I hope. You have 4 qubits, gates. Now you understand what is X, C naughts, Toffoli, and here they make the measurement, and you put the measurement on a classical bit, a classical register for qubit Q2 and the Q3. So let's do a hands-on, a practical here. and see if this circuit really implements the addition of two, the equivalent of addition of two bits. So if you remember the half, the classical half adder circuit, what is the table of truth? We have two inputs and a sum and a carry. Okay? So if you want to write it down or to rewrite it, 0 plus 0, because we have four possibilities here, 0, 0, 0, 1, 1, 0, or 1, 1 as input. Everyone agrees? And the result would be a sum and a carry. So in the case of 0 plus 0, we will have 0 sum plus 0 carry. 0, 1 or 1, 0 both give the same sum, which is 1 and no carry, 0 carry. While 1 plus 1, a binary, gives 2, of course, in decimal, but in binary, decimal is 10, 1, 0. So the sum is 0 and the carry is 1. Okay. So let's see if the quantum circuit simulates exactly the same thing. Start with 0, 0. Okay, try to do the hands-on practical with me. 0, 0. So you apply x to 0 here and you apply x to 0. What would be the result here? What does x gate? X gate is an inversion. So what would you have here? This is only a barrier for to better visualize. It's nothing, no action. Okay. If you understand how it works, it's very simple. Quantum circuit, all the others will be getting clear. So if 0 here and 0 here, what would I obtain here? State 1 and state 1. Okay? Good. So here I have 1, 1. Next, I apply a C0 gate with the control qubit Q0 and target qubit Q2. Stay focused. Which is initially in state 0. So what will happen to qubit Q2? It depends on the state of the control qubit Q0. If it is 0, nothing happens. If it is 1, the state changes. Or what is the case here? It is 1, so it is activated. So the state of qubit Q2 will be 1 here. So here, when we arrive here, we will have 1, 1, 1, 0. Okay? Next, we apply another C0 gate to qubits Q1 and the Q2. So it's the same thing. This is 1. So it will change the state here. And the state of the qubit Q2 will be, it was 1. It becomes 0. Okay? So I have 1, 1, 0. 0. Okay?
1, 1, 0, so therefore Q3 changes. Q1,
yes. So, yes. So when I measure here the state of Q2, what would I find? 0. I find obviously 0. Okay? And this would be the sum. Okay? So this is the case of 0, 0. And you can try the other cases, 0, 1, 1, 0, 1, 1. Maybe the most tricky case is 1, 1. Better to do 1, 1. So let's do 1, 1 together and then move to another example. So actually what we did now, I didn't say that, the exercise we did now is not the case for 0, 0, it's the case for 1, 1. Why that? I forgot to tell you something. How to create the four possibilities here? I'm sorry for that. How to create the four possibilities here? 0, 0, 0, 1, 1, 0, or 1, 1. How to create that? If I want to create 0, 0, actually I do not need the both X gates. I should start directly with 0, 0 here. Okay? If I need 1, 0, I will put X gate here to have 1 and nothing here to have 0. And the same thing for the other. And if I want to make 1, 1, I need 2 X gates. So what we did, the exercise we did was the case for 1, 1, which is the most interesting. So let's continue it as we started. So we arrived here. So what was the result for Q2?
0.
I don't remember anymore. So we said 1, 1. So here it becomes 1 and then 0. So we have 1, 1, 0. Here, 0. 1, 1, 0, 0. Then we have the Toffoli gate. So how the Toffoli gate? It's a double control. So if both are activated, it will change the state of qubit Q2. Or it is exactly the case. Both qubits are in state 1. As they are in state 1, the state of qubit Q3 will be 1. So what will I have? I will have 0 here and 1 here. So the sum will be 0 and the carry, as expected, will be 1. So you see that it works very well. Okay, understood? But still, I mean, do we really need a quantum computer to make a half addition? Not really, but it's just to illustrate how it works. So of course we need quantum computers for more complicated algorithms like the teleportation algorithm like this. Okay? So this is the teleportation algorithm. Let me, wow, so I'm almost done. I'm a little bit late on time. So in the second part, we will practice on a more sophisticated quantum circuit, which is the quantum teleportation circuit. So you will see how it works and what is the classical part of it. But just before closing this lecture, a few words about why either. You see here we have a classical register. You have always classical registers. I mean, maybe this is more important to say. When you imagine a future quantum computer, it will not be, I mean, the full thing will not be all of it quantum. Because we are not the quantum beings. We are classical. So we need some classical information. So in the best scenario, the quantum processor of the quantum computer will be a part of a larger device, which certainly will have some classical part, like a screen, like a keyboard, like output results, which will be then something we can, as humans, we can deal with. We cannot deal with wave functions and wave packets and eigenstates. We can deal with classical informations, zeros and ones, using the binary system to transform them to something we can understand. So that's why you always need some classical registers. So this is the point here, why we need the classical parts. And also, say, when you have some result, you want to share it. I want to send my results to Malik. So I have a kind of table or graphic or whatever. So when I send it, Malik should receive it also in this way, not in some quantum weird thing I cannot understand. Although in the meantime, I can use a quantum channel, but at the end, I have to have some classical information. That's why we need a classical part. Okay? So that's it for the first part here. You have some appendices. I'm not going through, just to show you. And as well, all the information needed for the gates I didn't mention here for a lack of time. Okay? And also another example, very good if you need some hands-on or practicals, the comparator circuit, how it works in the classical case. Okay. So, yes.
There's also a question.
I didn't see this. What is the real and simple relationships between quantum probability, quantum entanglement, and coherent state of systems, and their direct contribution to the quantum computers? What is the recent relation between quantum probability, quantum entanglement, and quantum incoherent states of a quantum system? Well, for the first part, before going to the second question, thank you for the question. First of all, then of course, quantum mechanics is probabilistic. So when you are using quantum mechanics to build up some device, you have to deal with this probabilistic behavior and to take advantage of it. So here, where the probability appears in the quantum computing, as I said a few minutes ago, is that when you make the measurement step, the last step in one of the circuits, I can show. Here, for instance, yes. When you make the measurement on qubit Q2, so of course here I reviewed the four cases separately, but imagine you do not know the states of the initial qubits, or the initial qubits Q0 and Q1 are not in well-defined state 0 or 1, but in a combination of them. The question is, what would be the result of the measurement of qubits Q2 and Q3? Of course, the answer is the following, that the value of this measurement is 0 or 1. This is in all cases, but the probability of the result will depend on the linear combination of states, of the initial states. So, when you make your measurement at the end, all what you get is some probability to have such or such result. So that's why you have to do the calculations many times. I said thousands of times at least. And this, I hope this answer addresses your question about the probability. For entanglement, entanglement is absolutely necessary to implement algorithm as, for instance, the teleportation we'll see in the next lecture. But also all the important algorithms in quantum computing, like Shor algorithm or other algorithms, entanglement is the main property, that makes quantum computation going exponentially faster than classical computation. Because using entanglement, you will see in a simple example with teleportation how it works thanks to entanglement and why it would not be possible without entanglement. So entanglement is in part with actually superposition responsible for the exponential speed up of quantum computing. So the second question is, if we imagine that the binary computers has two outcomes, yes, that's true, in 2 days, then what is the real potential and possible outcomes of quantum computers relative to these ordinary computers we use at the moment? Oh, I think we will always, or for a very long time, still need. I don't see who is asking the questions. There is a camera somewhere? Is this? Are they seeing? The name is Marissa. No, they don't see.
It's Marissa.
Yeah, the name is Rich. Okay, I trust you. So I'm sorry, I'm not seeing you. I guess you are not seeing me. But okay, let's play the game. So this is a good question. I mean, will quantum computers remove classical computers from our laboratories? I don't think so. At least for very long time. This is still very sophisticated technology for research and development, and for most of the tasks we do not need. To prepare my lectures, to make this PDF, do I really need a quantum computer? I do not think so. So don't worry for if you are in the business of selling laptops and computers, you will continue to make money with that for a long time. So how we can control the optical noise and fluctuation in the quantum gates? This is the big problem, of course. This is the main point. The coherence. The quantum states are very fragile. So the challenges, the hardware part, engineers and scientists are facing every day is how to fight this not only optical noise. Optical is for quantum computers using photons, but when you are using superconductors, you have to control the microwave pulses. You have to control the temperature, the coherence coupling with photons, etc. All the condensed matter physics. Okay. Thank you once again for these very interesting questions.
All what the description here, if indeed is related to electrons, as you were showing us with the processes, it does not surpass the same principle is applied for photons, isn't it?
Yes.
So we might think that standard semiconductor based or material based system, the microprocessor, operating with electrons, could be more or less duplicated, if possible, but using photons. Because the photon, and therefore to make an optical microprocessor equivalent. And the advantage is there will be this aspect of heat and so on, and therefore the coherence will be less intensive, and the speed of photons relating to electrons is far higher. I think my question is that this is a general description, this continuity description, even if it's applied for electrons, it must be valid for photons, isn't it?
Yes, but I have to be a little bit cautious here because showing the equation does not apply to photons. We need something else. So that's why I'm dealing with polarization. But still, quantum computers based on photons, fully optical, already exist as prototype. And they are very good, and they are room temperature running. And in the beginning of the lecture, I told you about the quantum advantage, first proven by Google team with this superconductor from Singapore. But few months later, the Chinese group using photonic quantum computer have shown also a quantum advantage in another very challenging problem as well. So this is one of the ways, and to build up the next universal quantum computer. And the question, which is the best candidate superconductors, trapped ions, photons, from atoms, NMR, other technologies, is still open. And the different companies are trying different things. And at some point, probably the technology will converge to one or two best candidates.
Just as Mark, so just as you highlighted, just 2 minutes ago, you pointed out condensed matter. And here we are dealing with, how can I say, superconductivity, heat, transfer, transporter, and so on. So do you think that the material science will play a pivotal role in this quantum computing thing?
Definitely. Not better than this morning. There was reading some news in the field, and there is a quick announcement by Australian team using the quantum dots. Quantum dots as implemented qubits, and they found a new mechanism to control the electrons with some electric fields. It's very recent, within the Nature paper just appeared a few weeks ago. So that we are hoping to be able within a few years to build up millions or thousands of qubits on the chip. And this will be fantastic. And this is nanophysics, this is nanotechnology, this is quantum dots, this is material science, this is all what you are dealing with here.
Let's then probably the next time.
We may take a short break.
Yes.
For the last part, I will not be very long. I will make it short so that you are free to go when you are. in which I will deal with quantum algorithms. So now we have the circuits. We know how to use the quantum gates to build simple quantum circuits. The question is, what next? What kind of algorithms we can implement, and what are those who are really interesting? Adding two numbers does not really require or need a quantum computer, but some other algorithms absolutely require quantum computers. Why? Because they are based on the quantum properties of superposition and entanglement. So far, several quantum algorithms have been proposed and implemented. You can find full lists of them easily on internet just by googling some keywords like quantum algorithms. So the most famous ones are, or at least part of the most famous ones, are the following. The Dutch algorithm, because this algorithm published in 1985 was the first one, historically the first one, to show an advantage of quantum computing over classical computing for a very simple problem. It was a kind of a proof of principle, and on the case of one qubit, and then generalize it to several qubits in what is called the Dutch-Joza algorithm. Some related, more or less the same idea, equivalent algorithms like the Bernstein-Bazirani algorithm, Simon's algorithm, and the quantum counting algorithm. You have also algorithms related with communication, including here in blue quantum teleportation and the quantum cryptography or quantum key distribution. In green, also a very important algorithms like the Grover's algorithm for search purpose on non-structured set of items or database. As well, very important. But as we said, the jewel on the crown of quantum computing is the Shor's algorithm. The Shor's algorithm is the one we discussed about yesterday, which is able to find the prime factors of a large number with applications to RSA cracking, etc. Okay, and you have also others. Maybe I can mention that the last one here is interesting for us, the variational quantum eigensolver. So this is the quantum equivalent of variational methods we are routinely using in quantum mechanics to find the bound of the ground state of several systems, like in DFT, you know about the DFT or other methods. And it is quite useful. We are doing some work on that in my university with our students, and it works quite well for describing molecular systems, either for ground or excited electronic states. So in this lecture, I do not obviously have time to show all of these. I make the choice to show you these two algorithms, quantum teleportation. It's at the same time very simple and quite impressive. It is interesting. And also quantum cryptography, okay? So this is the program for this lecture. The starting point is the following. Two partners A and B, generally called Alice, like A, and Bob, like B, but it can be any other couple of names. So Alice wants to send some information to Bob through a channel. More precisely here, we said she wants to send a qubit, Q0, to Bob. Actually, she is not sending the qubit itself physically, but she is preparing the qubit state. Let's take the example of only one qubit, and Alice prepares this qubit in a specific state, either 0 or 1 or any linear combination. Let's take the more general example, alpha 0 plus beta 1. Okay? And she wants to send this information to Bob. What does it mean exactly? It means that in some way, Bob has another qubit, and the aim of the operation is that the qubit in Bob's hands, call it Q1, will be by some transformation, starting from default state 0, will be in the same state as the qubit of Alice. It's not just a kind of duplication of the quantum state, making a copy of the quantum state of the qubit of Alice or the qubit of Bob. Very simple operation. So imagine the qubit of Alice is in state plus, so 0 plus 1 normalized, and initially the qubit of Bob on the other side is in state 0. Is there any quantum circuit or quantum operation that makes the qubit of Bob moving from state 0 to the state plus? It seems very simple, and we are tempted to say yes, it should be something easy to do. Actually, according to the quantum mechanics, this is not possible. Duplicating or copying or cloning a quantum state is not possible by a unitary transformation, so by a circuit involving only Alice and Bob. This is what we call the non-cloning theorem. The non-cloning theorem. This theorem prohibits this operation if the only parties involved are the sender and the receiver. So if we denote chi any state of the system A, it is not possible to clone it to copy it to a system B. Why not? So this is the well-established non-cloning theorem. I put it in an appendix, but I think I can go through. Why not? It would take like not more than, I would say, 5 minutes. So maybe it is worth doing it. Why not? So let's see the derivation together. The non-cloning theorem. Is it possible to duplicate the quantum state of a system? So we will suppose that it is the case. So let's suppose that system A, so the first qubit, is in state chi. So we will call the state chi A related to qubit A. And we want to copy this state to a system B, initially in another state, whatever it is. Call it phi B. In general, obviously, different from chi, from the state chi. So, if we consider the system including both qubits, now, A, B, this is the new system, the two particles together. If this operation is possible, this means that we can find a unitary transformation, so a quantum gate, that transforms the initial states where particle A is in state chi and particle B in state phi to another state where both qubits are in the same state chi. So A stays in state chi, and the B goes from an initial state, phi, whatever it is, to the wanted state chi. So if this transformation exists, it will do the following operation. Okay? Why this is not possible, actually? Because if such a gate exists, then it has to be independent of the state we want to copy. Like when you have, I don't know, a Xerox machine, you can make a copy of any document. It does not require only articles or whatever. Just to make a very crude comparison. Okay? So if I consider a couple of possible states of A, call them chi1 and chi2. So what should the transformation do? It should transform the state chi1a phi b to chi1a chi1b, and the same for chi2, and even for chi3 or whatever, or any other state. Okay. Next, as here we have vectors. Actually, this is a vector. This is a vector. We can make the inner products or the scalar products of them in two different ways. So, using the fact that U is unitary. Unitary means that U multiplied by U dagger equals 1. So if I move here from, I take the conjugate, so from the ket to the bra in quantum mechanics, and make the product from this side and later on this side. So for the left side, it will be, let me call this scalar product, this number, call it x. So it will be chi1a tensor phi b u dagger for the left part, u chi2a by phi b. And as I said, what is the value of u dagger u? It is unity, so it disappears. So you have here a simple scalar product that you can separate, that you can factorize, and it will give you chi1a scalar chi2a multiplied by phi b scalar phi b. And here, once again, come back to the question of normalization, it disappears because it's 1, and you end up with this first result, chi1a, chi2a, phi. So if now I do the same calculation but using the right side of the equations, this by this. So the same product will be chi1a, chi1b by chi2a, chi2b. And once again, I separate them, and it will be chi1a, chi2a by chi1b, chi2b. A and B are here only kind of indices related to the particles, but the states are exactly the same. Chi1 here is chi1 here. It is exactly the same. So this number is equal to this number, and both are equal to x. But what we find finally is that x equals x squared. And this is very, very limited. Actually, to only 2 cases, the roots of this simple algebraic solution is either 0 or 1. X is a number here. It can be either 0 or 1, which means that the only possibilities is that we have either the same state, chi1 is the same as chi2, or chi1 orthogonal to chi2, or I'm speaking French now. On the other hand, we suppose that chi1 and chi2 are absolutely arbitrary states. They are neither equals nor orthogonal, which means that this is not actually possible in the general case. Okay, so this is the derivation, and the conclusion of this is that such a unitary transformation, the universal one, does not exist. Clear? So it is not possible to copy the state from qubit 1 to qubit 2. And this is what we call teleportation. So the teleportation this way, it is not directly possible. So now what would be the solution then? Okay, the solution is to use entanglement, the magic of entanglement. How that? Alice and Bob call for a third partner, we call it here in the community of quantum computing, this character is called telemon. And telemon has enhanced a couple of entangled qubits, like the two photons used in Aztec experiment. And he shared this couple of qubits in an entangled state with Alice and Bob by sending one to Alice and sending the second qubit to Bob. Okay. So telemon sends a pair of entangled particles, or qubits, one to Alice and one to Bob. Of course, the state describing this pair of quantum entangled particles is one of the kinds you have already seen, like the Bell state, like 0, 0 plus 1, 1, or something equivalent. So this is the idea. Now, how does it work? How does it work? How to translate this in terms of quantum circuits? Okay, so let me maybe first show you, I think it's better to show you the whole circuit. Yes, so this is the whole circuit. You see, it is very simple actually. You have 3 qubits and 2 classical registers here, and a couple of Hadamard gates and a couple of CNOT gates and measurement. That's all. That's all you need. So why 3 qubits? So of course you have the qubit. So you have the qubits, the initial qubit that Alice has, Q0, in some state, psi, and the pair of entangled qubits sent by telemon, one to Alice and the other one to Bob. And the game is to copy the state of Q0 on Q2. To show that this way it is possible indeed. So if I have a look only at the first part and then the second part, just to make it more clear. Yes, so here the qubit, sorry for the screen here, it is Q1. So the qubit Q1 passes through a Hadamard gate followed by a CNOT gate. So we have seen this exercise in the first part. What is the state here? When we make Hadamard followed by CNOT. Just did it this morning. Yes, so we have seen that Hadamard followed by CNOT is the simplest way to create an entangled state. Okay? So this is how we create an entanglement in the quantum circuit. So here we obtain a state for Q1 and Q2, which is the entangled state, normalized 0, 0 plus 1, 1, a bell state. So this is, let's say, what is this simulates the job done by who? By Telamon. Telamon is creating the pair of entangled particles. Okay. Then Alice applies a C0 gate followed by, this is the C0 gate controlled by her qubit Q0, followed by an Hadamard gate on Q0. So what would be the result? So we will have some result, we'll review it later. And at the end, what is done is the measurement of the states of the qubits, the states of the qubits Q0 and the Q1. Done by whom? Done once again by Alice. Okay? So all this part is done by Alice. Where is what is the role of Bob? The qubit of Bob is Q2. Okay? And you will see, depending on the results obtained by Alice, what will Bob do in order to make sure that his qubit is in the same state as Q0. So once again, whatever the evolution here is, what are the possible outcomes? This is universal, it doesn't depend on the state. What I'm meaning is the following. When you measure the state of Q0, what are the possible outcomes? And what are the results, whatever is happening when you measure the state of qubits? What are the only two values you can have? On 0 or 1. So measuring the state of Q0, you can have 0 or 1, nothing else. The same measuring Q1, you will find 0 or 1. Okay? So what are the possible outcomes for both when you make both measurements? The four possibilities very simple: 0, 0, 0, 1, 1, 0, or 1, 1. Exactly. So the protocol is as follows. So Alice makes the measurement of the two qubits, and there is a code that Bob knows from the very beginning, which is as follows. After Alice gets her results, she sends the results publicly, classically, to Bob. She can just make a phone call. Hello, Bob, I found 0, 0. Or 0, 1, or 1, 0, or 1, 1. And it's a kind of recipe. Depending on what Alice says to Bob, Bob knows what he has to do to his qubit Q2. So, if the result of the measurement is 0, 0, in this case, Bob has nothing to do. His qubit Q2 is automatically in the same state as the qubit Q0, and the teleportation is achieved. If the result is 0, 1, he only needs to add an X gate, to apply an X gate to his qubit to be sure to get the state of the qubit Q0 of Alice. If the result is 1, 0, he has to apply the Z gate. Here, I hide the X gate. And if the result is 1, 1, he has to apply both Z and X gates. And in all cases, you can check that. It's a kind of simple exercise with my students. You can start. We do not have time to do it now, but what you can do is to suppose that the initial state Q0, the qubit of Alice, is in some superposition of 0 and 1. Alpha 0 plus beta 1. And go through the circuit using the rule you know now. about how Hadamard gate acts and how CNOT gate acts. And you can simulate the 4 cases and check that in the four cases, 0, 0, 0, 1, 1, 0, or 1, 1, in all cases, Bob, at the end of the day, ends with his qubit Q0 in the same state, alpha 0, plus precisely beta 1, the same state as the qubit of Alice. And that's the way the teleportation of the quantum state is realized. Okay? So this is the teleportation algorithm. The key point here is that this protocol obviously is not possible if you do not have this kind of magic property of entanglement. So if it works thanks to entanglement. And this is a very striking example, that's why it's very popular, of a simple quantum algorithm where you see the power of entanglement property to allow doing things that otherwise you cannot do without the entanglement. Of course, once again, because it can be a little bit confusing, teleportation here, once again, does not mean, because you know, like in science fiction movies and so on, teleportation means that someone enters some place, kind of box, he disappears from here, and he is reappearing on the other side of the galaxy, you know that. So we are not speaking here about the teleportation of matter, of particles themselves, but the quantum states. It's like making a copy at distance. It's like a fax. It's like making a copy of the state. Okay? So no entanglement, no quantum teleportation. This is the take-home message for this example. And this kind of it was theoretical. It was implemented for a long time, and in a very impressive way by this guy we spoke about yesterday, Anton Zeilinger. He won the Nobel Prize with Alain Aspect and John Clausen. I have shown you yesterday the work of Alain Aspect and part of the work of Clausen. But why Zeilinger got also the Nobel Prize? It is in part because he was able to implement physically the teleportation algorithm and making the copy of a quantum state on a distance of 143 kilometers. It's in the Canary Islands, with 2 sites here in both islands here, as you can see. And he was very successful with that. I have shown you yesterday another example, more recent, 2019, of the Chinese quantum satellite, sending the pair of, so this is kind of Telamon, and it is possible to make teleportation between the 2 ground stations. So you see, only this is not really only theoretical, but it can be implemented. Okay, now the very last part, another, at least a flavor of it, what is called the quantum cryptography. The problem is following. I want to share with Malik, I'm in Tunisia, he's in South Africa. I want to share some secret, very personal message between me and my brother and friend Malik. I don't want that anybody gets the information. So you know that this is not easy. If I make a phone call, someone can be listening somewhere. If I send a letter, it can be open, etc., etc. Is there a way that I make sure that my message is secure? What people do now, like for WhatsApp, calls and so on, as I said yesterday, it is based on a classical, mainly RSA protocol. It's really powerful. So to break the code, you need, as we said, to find the five factors, and it is not possible today. Although very recently, Chinese group announced that the possibility is coming sooner than we thought before. Anyway, So taking into account that someone can be one day able to break this code and to have access to the information. Is there any another possibility that completely prohibit any spy to get the information? Or at least, if it happens, the sender and the receiver know immediately about that and they can change the topic or we can speak later on. So this is what we will see. So the RSA, etc., how it is threatened. Okay. So I talked about all these. So how does it work? We are talking now about quantum cryptography. How does it work? Talking about the quantum circuits and the quantum cryptography, the information I will send to Malik will be the state of a register of quantum bits, of qubits. What does it mean? If it's a binary classical system, I will send him, the machine will send a succession, a word, it can be quite long, of zeros and ones, and when he receives it, he can decode it and decrypt it and make it more clear in some language. So in quantum, I will have to say a state. So let's see how it works. Imagine that Alice prepares one qubit Q, in the state plus. Okay, so the qubit is initially in state 0. What should she do to prepare the qubit in state plus? You know what I'm saying? Hadamard. Lovely. So she just applies Hadamard, so she gets a plus state. Okay. Now, the plus state actually is the eigenstate of the X gate. What does it mean? How to say that in very simple words? Okay, let's imagine that the 0 and 1 are two vectors like this. Okay, the Hadamard is simply a rotation of these two vectors by, let's say, by 45 degrees. It's not exactly that, but it's not rigorously that, but let's take this picture. Okay? And we measure the state, which means we take the projection of the vector on a given axis. Okay? So if the sender and the receiver use the same axis, they will find the full length of the vector. But if they use different axes, they will not find the same length. Okay? So this is what we call using the same basis or not. So if Alice prepares the state using a Hadamard gate, so in the X basis, and Bob uses the same gate, he will, you can check this very easily, he will find 100% with 100% probability the state in the state plus, which means 0 of X gate. I mean, both bases agree. This is the good case. Okay. Okay. Now, yes. Now imagine that some spy is in between, is trying, because I have to explain how it works, how a spy will intervene here. The spy, called Eve, will try to measure the state of the qubit in between the sender and the receiver, to get the information for himself or for herself. She's called here Eve. Thanks to the quantum properties, in particular the wave packet collapse postulate, the measurement destroys the state because it makes the projection, so it changes the state. Then, by changing this, and if Bob is not using the same gate, he will not anymore get the result with 100% probability, but only with 50%, because it can be half, you have 0.5 probability for the state to be in state 0 and 0.5 probability to be in state 1. Okay. So in this case, they both know that someone is listening. So how it works? In more details. First, so this was the illustration with only one qubit. So now for a more realistic case, Alice is preparing some message, a word, let's say a word, coding a word on a register, let's say with 60 bits, classical bits. It may be much larger, but this is just to illustrate it. So it's a succession of ones and zeros, meaning something. Okay. This is the message she wants to send to Bob. Then she prepares, so she has 16 qubits, a register of 16 qubits, and she prepares each qubit according to the value of the corresponding bit. So the first here qubit will be prepared in state 1, the second in state 0, etc., up to the last one. So this is the state of the register of 16 qubits Alice wants to send to Bob. Second step, Alice makes a choice of basis, which means that she decides or not in a random way to apply Hadamard gates to some of the states or not. Z means that she stays in the first basis as Z is diagonal, and X means that, for instance here on the third qubit, she applies an Hadamard gate so that she will be in the basis, on the rotated basis of the X gate. Okay. Bob, until now, does not know about the choice of Alice because he's far away, and this operation is done by Alice by herself. Of course, Alice keeps these informations for herself. The message, obviously, and also the set of gates she is using. Second step. So Alice applies the gates to the register. So what would be the result? So of course, Z does not change the state, so Z applied to 1 is 1, Z applies to 0 is 0, but X, which means Hadamard behind X is the basis. The transformation used is Hadamard. Hadamard applied to 0 gives a plus, etc. So this is the transformation operated by Alice. I try to make it simple, but I'm aware that it is a bit tricky and technical. So at this point, Alice sends the message to Bob. Okay. The third step, Bob measures the state of this. Bob does not know the sequence of gates used by Alice, as she has chosen them in a random way, and she kept the information for herself to protect that information. So what will Bob do? Actually, his only choice is also to choose another random set of gates, Hadamard to be in the X basis, and Z to keep the same basis. So we have from both sides two random, in general, different sets of gates to make the measurement. So what are the possible outcomes? If for a given qubit, by chance, because it is random, Alice and Bob use for a given qubit the same basis, so the same gate. Bob will find the same result with 100% chance. If not, it will be 50%. So he knows what are the gates that gives him the same result as Alice and what are the gates that do not. So the next step is that Bob and Alice exchange the basis that each has used for each of the qubits, so all of them. I mean, Alice shows publicly or shares in non-secure channel. She doesn't care actually because it's useless information for any spy. The both sets of gates. Why it is useless for the spy? Because the spy does not know the initial message. He cannot do anything only with the sequence of gates. So as I said here, if they are using for part of the qubits the same gate, they will obtain the same result. Otherwise, they obtain different results. And in the fifth and last step, before that, Bob will retain only the gates that have given him the same result. So this will be the key. It will be reduced. It may be instead of among the 16 initial gates, maybe 7 or 9 or 6 or 12 will be good for them. And Bob and Alice will share part or all of their keys, and they will use that. They will use that as a secure way, because for a given gate, they are sure now that they are using the same basis. So the expectation is the following. If Bob measures the state of that qubit, he will find with 100%, of course he repeats the measurement several times, as I explained for all the quantum circuits principle of working, he will find a kind of histogram with 100% of a given value, 0 or 1. If not, he will be sure at that time that someone is spying, because while spying, the state of that qubit will have changed in the meantime. Okay? So this is how it works. I apologize if it's not clear enough. We have to practice to take an example and to go through the circuit. But just to give you a flavor maybe of the way it is working on. And nowadays it is not only something theoretical or in the textbooks or the university for teaching. It is used, devices already exist for quantum cryptography. Very recently, Malik, on the occasion of the visit of French President Macron to US, they exchanged a very first message between Washington, D.C. and Paris for the Department of Foreign Office. A message, kind of confidential message, using secure protocol using quantum cryptography. And it will be certainly the technology used in the future like all the, for all the, let's say, sensitive matters at the international level. Maybe the very last point here, I'm done. But just to let you know that the consequences of all this technology go far beyond the community of physicists. It concerns everyone. It concerns the society. Here, I found this paper a few months ago. It's a lawyer review, and several lawyers are already preparing the legislation and the legal framework to prevent any possible conflict or any possible cases resulting from the use or the misuse of quantum cryptography or quantum technology in general. Okay, so I hope that with this very short introduction to the field between yesterday and today, you got something in hands, you understood at least the principles. Some points has to be worked in more details. So maybe I am over with my lectures. Let me, if I can switch to the screen just to show you a couple of things more. I have seen that you already entered this group. What I'm going to show. So there are many free platforms where you can find good tutorials and hands-ons and several practicals. Yes, thank you.
Just to add on what Dr. mentioned,
Sure.
that is that all of you, or now from there, each dissertation, unless you report specifically the PhDs, all of you would be obliged to have a chapter on quantum computing. All of you, without any, exception. And in addition, that quantum computing, we should sense that you grasp the essence of quantum computing, one, and secondly, that you will apply it. You will come with some material. One of the materials that you are investigating should be applied somewhere, how either in terms of superconductivity, heat, transfer removal, and so on and so forth. Sorry.
Yes, thank you. I have the idea, but I'm afraid that you will hate me.
No, they will give completely the right and the
additional work, maybe you don't focus.
No, absolutely not. It's a really a must in their CVs. Thank you.
So maybe if you include it in a more, if I may,
yes,
the more general field of this, how to call it, disruptive technologies, including artificial intelligence, machine learning, quantum computing, and all these, may be useful, certainly, very short paragraph, to make the work more light for you.
Yes, absolutely.
They are very kind with me, so I do not want to mess with them. Okay, so this is the IBM Qiskit platform. Very well done. You do not need a lot of things. You can do most of the work online, remotely, but you can also install on your personal computer the software. If I go to the learn part here, also you find a lot of resources, a very good introduction. I used some of the material. You will recognize some of the pictures I've taken from here, as I acknowledged it before, going even to the quantum machine learning, which is really trending now in chemistry. To the, for instance, if you go to the quantum protocols, you see you have resources here for most of the protocols. If I take the example I have shown you here for the quantum teleportation, yes, maybe it's even more clear that this is, you recognize this graph, and so how you can code it, people interested in coding using Qiskit, this is Python like codes with the libraries, etc. And you can run it, you recognize here things and how it works. For instance, the details of you recognize this, okay? So all how the protocol is working, and even more things, some examples of arbitrary states, illustration on the block sphere, etc. It is very, very nice, and I'm using it for teaching, for the practicals and hands-on for my students in Tunis, the kind of histograms you can have, etc. Okay? So that's it. Thank you very much.
Let's stand up and do the audition. Can I say, the students have all the fellows here have, I wish that next week I will speak with them and I will get their appreciation and find out how we could implement this series of lectures in the future. It's extremely critical. These are new disruptive disciplines for which we are obliged to digest and really inform, in addition to machine learning, artificial intelligence, and so on. I think you're going to need for intrinsic important backgrounds of these emerging fields. And it will be incorporated in the training in the state organization for the PhD. And we will technically rely on you after these lectures, and we will definitely interact with you, and certainly we will certainly rely on you from the external peer reviewing process. I think at least this section we would certainly approach you from the university side point of view and request coming from you to peer review this section of this PhD for the fellows. Thank you, thanks a lot. And we will keep in touch with Bob whenever the lectures I have in this week are available to us. I'm sure that they are with my son will send to all of us, my son. And how can I say, and whenever you use them, please do acknowledge Bob, being the publication, being the thesis, or being the talk. Whenever you do courses and so on, please acknowledge Bob in that regard, and you are entitled, of course, to interact with him directly in our college.
This is a very good practice to mention. You are nothing that I always acknowledging sources I'm using.
Yes.
And this is the best practices we have to follow. Always mention, because we are not expected to invent everything. We take things and make from them something different and more useful.
Thank you. And Prof, I think what also you have mentioned with your theoretician by training, that you have always kept us refreshing our memories and reminding us that how can I say, material science and universal matter is a really emerging superconductivity, nanotechnology, temperature and heat treatment, heat management, and so on. And I would like to see how the first qubits were achieved by implantation, by accelerator implantation in time, whereby there are some nitrogen, how can I say, nitrogen vacancies and so on. And myself here is an accelerator, and I'm glad that our fellow what do they no. Yes. Is here, and I will definitely ensure that from the ESAC point of view, we try to always come in and touch on the country. Thank you so much. We took a photo yesterday, so thank you. Excellent. That's a very
Thank you very much. Thank you.